Hi, everyone, and welcome to the first keynote at CRV 2020. It's my incredible honor to introduce John Howe. John is the Richard Cockburn McLaurin Professor of Aeronautics and Astronautics at MIT. John has Canadian lineage. He moved to Toronto when he was 10 years old and did his BA at the University of Toronto. And for the record, he told me that he still cheers for the Canadian hockey team at the Olympics, even though he's been living in the US and is actually now a US citizen. So I think that's all that really actually truly counts. John did his master's at MIT in 1990, PhD finished in 93 on robust control and design, did a postdoc at MIT, and then was an assistant professor at Stanford from 94 to 2000, and then moved back to MIT as a professor and has been there ever since. It's almost hard to know where to start with the accolades and awards. John is the founder of the Aerospace Controls Lab at MIT. He's an IEEE and a AAAI fellow. Numerous best paper awards at top robotics and control conferences, the editor-in-chief of IEEE Control Systems magazine, and over the course of his career has made many fundamental contributions to aerospace, robust control, mobile robotics, aerial robotics, SLAM, motion planning, and now even Summit RL. And so without further ado, I'll hand it over to John, who's going to talk about navigation and mapping in uncertain environments.
Great, thank you, Liam, and welcome everybody. It's a distinct pleasure to talk to you today at the conference on computer and robot vision. And again, what I'd like to do is to talk to you about navigation and mapping in uncertain environments. This is work I've been doing with a bunch of different collaborators, and you'll see their names pop up during the course of the talk. And if you're interested in looking at further research, you can take a look at my webpage, which is down here, and or take a look at the lab webpage. So again, as Liam said, it's the Aerospace Controls Lab. And you'll see that connected to my webpage as well. So before we get too deeply into a lot of the other topics, I just want to give you some of the highlights of the things that we have been doing in the lab, and these are things that I won't be saying too much more about, but if you're interested in, you can certainly take a look at the webpage. So one of the things we've done recently is formed a very large new flight space that we have, and you see here some of the robots flying around in it. This is Vicon based, as many of you see me probably doing work in that domain before. These vehicles are actually using VIO based formation flying, so they're doing their own internal sort of determination of where they are. And that's part of the reason why we have these carpets on the floor, so they can help do the localization. The other kind of domain space we've been thinking about, though, is not just quads flying around, but robots flying in or driving in. This is actually Building 32 on campus, trying to operate in a socially acceptable manner in an environment with people. So you do both sort of social acceptable work, plus over here we're looking at some of the collision avoidance. This is a bunch of sleepy grad students walking around late at night getting ready for an ICRT submission. The robots trying to navigate around and do some collision avoidance here based on some deep RL handling some of the sort of both detection and avoidance of the people in the environment. So these are actually, this is using a Velodyne. This one, middle one here, is using a Velodyne for localization, but it's vision for navigation, and similarly with the one over here. Another topic that's more recent and has connections to the recent announcements made by NASA in terms of where things are going. This is actually doing terrain relative navigation on the moon, looking at craters as a mechanism for determining where the vehicle actually is as it comes in for precision landing. So these green dots or green circles are all correct identifications of craters on the moon, from which, if you have a prime map, you can then do relative nav. You've probably seen lots of videos of quads landing on moving vehicles. So I challenged the student to actually make it a little more interesting. So we're driving here with our leaf blowers on the front of the truck. So we're actually trying to land in sort of a high wind environment. We've got wind here on the order of about 6 or 7 meters per second, which if you've flown a quad before, you know is a pretty excessive amount of wind. So it's landing on moving platforms with wind estimation on board, trying to do the actual adaptive control and landing in that type of environment. Last topic is one I wish I could say more about because we have some excellent work going on here in collaborative SLAM. So a lot of the work in our lab, similar to what's going up here on top left, is multi-agent work that we do, and you'll see me talk about some of that today. Here we're looking at a situation where we're driving around in a Unity sim, and basically now trying to figure out where we are in a navigation sense, but actually running a distributed postgraph optimization where as the agents realize that they're past similar locations, they can then actually sort of do feature sharing and snap the grid and actually come up with better estimates of where they are located. You saw one of those occur just there in the map. So it's classic of the sort of the SLAM plot showing how things get better as we can do loop closure. But the point here is we're actually doing loop closure between the vehicles and running this whole thing in a distributed fashion. So that's this video was made last week, so this is very fresh off the presses, and there'll be some exciting more stuff coming out over the summer on that. So that gives you a flavor of the types of things we've been working on in sort of a big picture sense. What I want to do though is today talk about some of the challenges we've been facing in doing autonomous flight, limited field of view sensing, typically handling situations where we have an unknown environments. So the types of challenges we've been looking at are how to navigate and fly or possibly drive quickly in unknown environments with limited perception range. So the world is going to be revealed to you. You want to try to maintain some safety. Obviously need fast reaction times to make sure that the system can actually respond quickly enough. But this is the entire navigation loop now. You're in a situation where you have both the perception, you have the planning, you have the flight control, and then of course the vehicle dynamics. And all of this has to work in sort of a symbiotic fashion where you're not spending an inordinate amount of time making giant maps on which, but it takes too long to actually respond to. So computational tractability is one of the obvious challenges here. You're going to do a lot of planning and optimization. Can you do it fast enough? All right, so we'll talk about this topic. That's thinking about what happens if you have limited perception range. The other question then becomes, what happens? Is there a way to actually think about how you go beyond that? And so the challenge here is to think about whether or not we can use contextual relationships of the things between the things we can see to infer perhaps what's going to happen in the future. And we'll talk about a topic here related to delivery robots. The final topic, we'll get back to the multi-agent work, and is thinking about an environment, trying to come up with a common environmental representation between multiple agents that have perhaps disparate views or observations of the world. The question is, how do you align these? How do you then go through the process of fusing them? And so the alignment here is focused on just making sure everybody's on the same page. We're talking about the same thing. And then the fusion is relatively straightforward once you've done that alignment, but the alignment step has to happen first and also has to happen pretty much every time you want to do a fusion. All right, so I'm going to talk about each of these three topics, probably for about 15 minutes each. And I think if there's any questions, just type them in the chat and Liam will jump in. And of course, we can take time at the end to answer some longer questions. So this is the first topic. It's called FASTER, great acronym. It's fast and safe trajectory planning for flights in unknown environments. There's a couple of QR codes down here which get to the paper. The code has been released as well. A bunch of these papers are in archive and coming out in conferences as well. But basically, for this type of problem, we're thinking about domains in which you have situations where the environment is certainly perhaps was well known, but through one disaster or another, has now become sort of cluttered and less well known. And so you're in a situation where you'd still like to be able to perform rapid flight in an environment where there is some structure, but not much. And so in that type of environment, you want to be thinking about high-speed navigation, maintain the safety so that you can get back to the base, and ideally do this with onboard perception. And you'll see us focusing on mostly the perception part of the problem as opposed to the navigation. There's a lot of other people have thought about onboard navigation. We're thinking more about, if we know where we are, can we determine where everything else is, and then handle the planning in that environment with that limited perception range. And so so one of the challenges that you face when you're doing this type of thing is you're sitting in a world here. So there's sort of, the classic work that I would have done of the past when I was, say, working in planning, which I'm going back maybe 10, 15 years now, just prior to really when we started working on the Urban Challenge in 2007. My view of the world was, someone give me a map, you tell me what's known and what's unknown, And so this is sort of the orange here is thought about occupied known. Then there'll be sort of the free known. And the premise is that, given that world, I can just plan a path from A to E and life is good. The problem is you realize when you start working with real robotics going on the field, that's pretty unrealistic. It's unrealistic you would know everything. It's unrealistic that someone will be able to give you a map of that thing and that would be meaningful. So the question then becomes, in the way that often sort of robotics experience the world, is sort of maybe the white space, which is going to be free. The orange would be then the occupied known. But then there's a giant amount of unknown space. And so this blue here is a question of, so Liam, my screen keeps saying my connection's unstable. So I'm assuming you're going to butt in if you can't hear me. Is that correct?
Yeah, everything looks okay.
Okay. And okay, good. Sorry, it's just it pops up on my screen, and so in this environment, one could just plan to stay in the free space, the occupied sort of free known space, this white space here. This will end up being safe because you're not venturing into the unknown, but of course it's going to be slow. You're just sort of very pedantic and you're constantly thinking about, if this is what I can see, this is what I know, then I'll just stay there. And so you sort of have a very short horizon and you're planning in that space. The alternative, of course, is just blast right into the unknown space and hope for the best. Of course, the situation could be one of discovery of a new object, which then requires maneuvers which are beyond the feasible capability of the vehicle, which is going to be fast and unsafe. So the thing is, how do you generate fast and safe trajectories? And I'll go through a little bit more detail, but here's the gist of the story. Is what FASTER tries to do is to maintain that contingency path where you're enabling it to plan both in A to E. So you're going to plan in both the free known and the unknown space. So you allow it to venture into that space, but you always maintain a feasible path here, which is ARF, which is the blue line, which is going to be in the known space, known free. And so this will end up preserving some of the fastness associated with the red design. It's heading in the right directions where you want to be, but maintains the safety of staying in or having a backup plan that's here. And what you actually publish, of course, is neither the red nor the green. You're going to publishing the blue, sorry. You're going to publishing the green. And by publishing, what I mean is that's what you intend to follow. And if you have a situation where there's a problem, by the time you ever get to about here, then you just follow this path and stay within the safe. And so basically what you end up having to do then is design two. You sort of design the whole path, the red one, and design the blue one, which is the sort of the safety guarantee. And again, the constraint is that the blue stays inside the free known, the sort of the free unoccupied space, the green here. And whereas the red can venture, it's obviously not going to go into the orange, but it can stay in either the white, the free, or the known free space, and it can go into the unknown space. And so by doing that, you can maintain both the safety that we'd like and the high speed or higher speed that you'd like to maintain. And like I said, you commit the green and then go with that as the plan, and it guarantees safety and guarantees speed. So that's one of the, that's the sort of the high level view of what happens. Then again, the nitty gritty of, okay, so what actually happens? Now, if you've done work like this, you're probably not too surprised. This ends up looking like a mixed integer quadratic program. At the end of the day, you're planning this red path here. This is our design over here. You're choosing these points, the blue ones. The world is being the world you're going to plan into is broken up into these polytopes, the green ones here. And the constraint is that basically you want each of these these blue dots to end up inside one of these polytopes. So when you do this, you sort of have two problems you have to figure out how to address. And so like at a high level, it's like you need to create the polytopes. Turns out that's pretty easy. Just in a world in which you have, even as you're discovering it, and you'll see computationally, this ends up being a really small piece of the puzzle. But you'll create this polytopic representation of the world that's free, that's known to you, and you're then planning a path in it. You then have to decide what that path is going to look like. Here's the giant MIQP. Anytime you see an MIQP, you're going to end up seeing things like this, the binaries over here. And you always want to be cautious about how many binaries you have. There's different types of approaches here. One is a somewhat conservative, where people end up with not too many of these sort of knot points, these blue dots. They end up typically being a different delta T apart, but they end up with a slightly easier formulation in terms of how to describe So they end up with sort of this section inside this polytope, this section of red line and this polytope, and so on. And that's the decision, that's sort of the heuristic they end up using. Our approach ends up being a little more complicated. It's a situation where now we have more blue dots to arrange. That's n here, then polytopes blue, and we have to deal with the integer variables. But basically what we're able to do then is have a much simpler choice of what the timing is. And this tends to be the trade-off, that basically we end up with a more complicated formulation because we use the integer variables to denote where the path is in each of these polytopes. So that complexity increase for us, but we have a constant delta t, and so that's a great simplification. Over here, choosing delta t can turn out to be quite complicated. So that's sort of part of the solution. You'll see, and anytime anyone talks to you about an MIQP, you want to be thinking about the number of binaries. I've been working with mixed integer linear programs now for over 20 years, and these are like a nice way to write down the problem. You always want to be super careful how many binaries you've introduced. And so while I talk about n greater than p, and n and then is going to control how many binaries there are, but you'll find that p is going to end up being quite small. And so n will be bigger than p, but this is on the order of 3, this is on the order of 4. And so the number of binaries will actually be quite small in this formulation. So in terms of computation, you'll see it actually scales reasonably well. We still have to figure out what this time is, though. We don't know what the time is along the path. So the first thing you build is the path. But there's no sense of time scaling here. It could be it's just a path in space. I haven't decided how long it's going to take me to fly it. So the thing you then have to pick is essentially each one of these blue dots is a constant delta t apart. I have to decide what that is. This ends up being a search. Now, we have a pretty good idea of what the number is going to be, so we're not just searching up in sort of never land and have to do lots and lots of iterations. We have a pretty good estimate of what it is. And the point is that we can actually try a different number, and so this effectively becomes a line search on delta t. And we try and fail, try again and maybe fail, try again and fail, but then find a delta t that works. And that may seem like a bit of a strange thing to be doing in real time, but the point here is that each one of these try and fail only takes about 4 milliseconds. And so most of the time what happens is that we can get all this done in about 15 milliseconds. And this is the bulk of the work when we're actually doing this path design. So this part over here is simply just figuring out what the path looks like. This is the part that tells us what it looks like in space-time. And like I say, this is sort of one iteration. You go to the next time iteration, and again, you have a pretty good estimate of what delta t is going to be because you've already done a lot of work. And so when you go to the next iteration and replanning in real time, you can now just start from that delta t, try a couple iterations, and you'll find that you don't have to do many iterations over time. And as a result, this 15 milliseconds, even that is a pretty conservative estimate how long this process is going to take. Okay. So typically then, you sort of fire up a problem. You have an algorithm, you fire up a hard problem. You get a bunch of different algorithms you download offline, and you take their code, you take the algorithms, you run them. You start charting things like how successful are they? How long is this going to take? And this is what I was saying before about the number of polyhedra. This is P. And again, 3 or 4 is a reasonable number. You get higher than that, the computation time does start to become sort of more above 50 milliseconds than we would like. So we tend to operate in this range right down here. And so what we're looking at, and again, remember, we have to do 2 path designs, the red and the blue. One's about 20, one's about 15. But when you compare what we're doing in terms of, and this is just distance traveled through the sort of pretty ratty looking forest here, we're actually about somewhere between 8 and 51% shorter in distance than some of the other algorithms that exist out there. And these are recent ones from recent robotics conferences. So that's a discussion of distance. When you actually look at the algorithm, this is it flying through the environment. You see on the left here sort of what it sees. And again, remember, the premise is that we know where we are, but what's around us is getting revealed on about this scale. So we're sort of flying through all these blue things, and we have no idea what's going on, and we're discovering it over here. What's mapped over here, and we're creating in real time, is that sort of occupancy grid. And so you get a sense of the orange stuff, that's the known occupied, and then the blue then ends up being the unoccupied. And I can sort of run that again, I hope. And you get a sense. And all this stuff that's going on in front of the robot over here is all the polygons and all that discussion of how to do the polytopic representation of the world that we're actually planning through. And you'll see several situations here where it's trying to find its way through narrow gaps and things like that. It's able to do that quite successfully here. So this is a hard problem, but not super challenging because it doesn't have a lot of bug traps and sort of dead ends. And of course, if you've done a lot of work in path planning, you know that that's super hard. So we've tried other types of algorithms and environments where we create sort of bug traps, things that has to find its way through. And one of the things we're looking at here is not just whether or not the thing is shorter, but actually whether or not it can actually go a lot faster. And in fact, this is us comparing with our paper from about a year and a half ago. And you'll see in the color scale here just how much faster we're going. So while the distance isn't greatly different, the time to actually perform the mission is a substantial improvement. And so that's the sort of just one environment. We've also tried this other environment. I'll show you a video of this in a second, the office. And this is a lot of bug traps. And it's a typical situation where as you're driving down a corridor, you want to get over here. So you have a sense of a goal sense, I'd like to be over here. But the result is you often end up going into rooms. You're driven there in a global sense of I'd like to get to the goal, but you don't realize it's a dead end until you go into the room, drive around a bit, and then realize you can't get out. And that's what this looks like here. And again, same sort of map. You've got a sense of what's happening above. The robot doesn't see this, of course. What it sees is over here on the left. Not a lot of information provided. And then this is the bug trap. This is the room it sort of went into, realized there's a problem, came back out. And it has this sort of local map that it has around it in which it can plan. So it's actually planning in that little tiny map of that known, unknown space, sort of the known space, occupied and free. And so when it gets into bug traps like that, it's able to just sort of back out through that plan. So that's all cool. And in this sort of pandemic world, you have to do a lot of simulations. But just before we did that, we were able to do some experiments. And so again, we're flying here in the Vicon space in our lab. So the vehicle knows where it is using the Vicon, but has absolutely no idea what's around it. So all these obstacles and all the other things that are in the world, it has never seen before. It has no idea what this map looks like. And we just telling it to zoom from point A to point B and just experience the world, as it sees it. And you'll see it's got a pretty high bandwidth attitude controller. So it looks jittery to the human eye, but that's because the attitude loop is just cranked up really high to make sure that it has enough controllability over the roll axis in particular and pitch. Give you a sense of scale here. This is carrying a Nook, which is an i7 brick. Which is an apt name, because if you've ever tried picking up one of those things, you realize how heavy it is. And so that does disastrous things to your roll capability for this vehicle. So the fact that we're able to do onboard computation, running Gurobi, doing the mixed and quadratic programming, all the onboard sensing using RealSense, have all that functional, and still be able to be relatively agile in that space is great. And again, I mentioned before computationally how things are going here. I mentioned these numbers before about sort of 20 or 15 milliseconds. But the decomposition part I sort of indicated was really tiny in comparison, and it's down here. So this is that part that says, given the world as is being revealed to me and the current local map I have around me, let me do the decomposition in the polytopes. And you're looking at numbers on the order of 3 or 4 milliseconds, very, very tiny. This is the simulations through the forest. This is the real experiments. And you see the numbers here on worst case, do tend to be a little bit higher, but still in the range of 20 to 30 milliseconds. So again, I think what we've been able to show here is through simulation and experiments, sort of being able to speed up to about 8 meters per second in that world in which we again know absolutely nothing about what's around us. And we're shown through the simulations and comparisons with other techniques, a significant amount of improvement of flight time and distance. One of the things that, I'm not sure what happened there, we've been looking at recently then is that's the single agent world in a static environment, relatively static. So the challenge was how to create a dynamic world. So we have a combination here where we have all the static stuff and then all these red agents just flying around us. And then we're the agent here trying to fly through all this mess and get from point A to point B. It was constrained to stay inside this channel, so I had no choice of sort of flying outside. And you can see just how complicated a world that is. And so again, you've got a lot of mixtures now of trying to accelerate through gaps and find your way around things when things are moving. So of course you can't map them very well at all. And once you can do that with a single vehicle, of course, then the challenge is how to take that to multiple. So this is now each one of them essentially running an algorithm in parallel. and again, discovering the world. But part of the discovery is not just the static objects and the dynamic objects, but also the other agents that are moving around. And so now you have a situation where you've got to start thinking about how to take faster and move it into the multi-agent domain, where now there's an aspect of sharing information in this case. And so this is brand new work. It's sort of, these are actually done last night. But it's new results coming out, probably submit to occur next year. All right, so I mentioned before, and I showed sort of a short video of this. This is sort of a different part of that video. This is the robot driving through the environment. And so we've done a lot of work on collision avoidance, path planning, but we're mostly planning in a world here where we have sort of a finite horizon. We're just planning in that horizon and able to then navigate and do collision avoidance. But one of the challenges that we want to start thinking about was how to move on to help out in terms of handle some of the situations, and this is work done with Ford on some of the what we'll not describe as sort of first mile, last mile, but the last 100 meters. And so it's not a big surprise. A lot of companies are thinking about autonomous vehicles and dropping off smaller delivery robots that then have to actually do the delivery. But you might get instructions like go to the front door, which to a human means something, but to a robot is a relatively useless piece of information, because it requires knowledge like where is that thing. And so without necessarily having a prior map or being able to map what this environment looks like, the question was, well, the issue of those types of instructions are intractable to maintain in all possible environments. So the instructions themselves have no geometric meaning, which is sort of how typically these robots would represent what this world might look like, and in part because we don't even know where the coordinates and appearance are of the destination. And so what we were looking for then was a way to use prior knowledge to try to put the visible information, i.e. so if you drop the robot off and it sort of sees this, but in here you might have a sense of this is the road, this might be the driveway. Can it use that information and some of the information perhaps provided by the larger vehicle to then to discover how to get to the door? And again, with the premises are we're working in pretty structured environments. We don't necessarily know what every house looks like, but we are working in environments where we can presume that it's a neighborhood that looks like this. And so there's a general sense of what a house in this environment might look like. And you'll see us use that knowledge as we go along. So again, just to put some structure into the problem statement, we have sort of a sense of the world, M, and a goal in it, but the goal coordinates are not known a priori. I'm not sure that's happening, sorry. Just jumped. The problem is that we only have a partial map of the world, and in particular can't see the goal at this point. So this sort of M partial is the thing that's observable to us is in white. We're sitting over here. We can't necessarily see that goal. And so you have some states then that are observable, some states that are hidden. And of course, part of what's hidden to you is the location of the goal coordinates. And so it isn't a classic planning problem. It's not like get from point A to point B. It's drive to where you think B is, but you don't necessarily know. And so, of course, part of this becomes discovery. You have to do exploration. And so ideally, what you'd like to be able to do is to learn a policy from the current state that we're in, that it does collision avoidance, is not whacking things. On the other hand, it's minimizing the amount of time that actually gets to the goal, even though we don't actually know where the goal is. Okay. So of course, if you had knowledge of the goal coordinates, then it is a planning problem. You just fire up, RT star and life is good. You just plan through there if you knew what the environment looks like. And even if you didn't, you could discover that as you go along. Since you don't, you're going to end up doing a lot of exploration, right? So you could build up a map, which would be fine, except for the fact that it ultimately leads to a relatively slow time to the goal. You might have a great map, but that wasn't my goal. My goal from an economic perspective was to get to the goal relatively quickly and do it safely. The map is perhaps necessary for that, but not required. So the literature then suggests trying to use context to help guide the exploration towards that goal. And different sort of algorithms have been thought about. Won't go into a lot of detail here, a bunch of references given as to the things that we've been looking at, but both graphical models and deep learning have been looked at. The issues that we saw was that the graphical models are interpretable, but tend to lack knowledge of geometry itself, whereas the learn models just end up being too general, and that's not useful for this particular application. So the particular challenge that Mike, the student, was looking at was not just how to do the end-to-end learning of get straight from an art, sort of depth, RGB depth stream here to the action and do the full end-to-end learning that some groups have done. I apologize for the bells. And so that's one approach, is just learn that policy. The alternative, though, is to recognize that we have a lot of technology that already exists in the world. So we can take the stream of data, run it through SLAM, generate occupancy grids. We already know how to do optimal planning, and we can do cost to go calculations. And the question then that we were trying to think was, is there a way to come up with an easier learning problem that is really just trying to find the mapping from the occupancy grid to the cost to go, recognizing that if we can do this part of the learning, which is the hard part of this particular problem, then we can take advantage of the technology that exists over here, technology that exists over here, and then just fire up essentially any MPC planner using a SLAM algorithm. And we just have to learn this connection here between the occupancy grid, i.e. what's around us and where should we be going, which then gets encapsulated as a cost to go algorithm. So that's essentially what happens here, is that basically the premise is we have a mobile robot. It's going to be running a SLAM algorithm, extracting sort of not working on the raw data, but a sort of a sense of what's around us in terms of the sort of lower dimensional representation of that world in the classic way one would be doing mapping. But it's going to end up being sort of a semantic map. And so we will have a sense of what those objects are in a semantic, so sort of where they're located and what they are, which is then captured in an octomap. And then we sort of scrunch that into a 2D map that ends up looking like this. And again, the key part about this is all partial, right? It's a partial semantic map. We're driving around, we've seen some things, we've discovered some things, we've estimated where they are, we've semantically labeled them, but in no sense we have any idea globally what's going on. And quite likely we've still not seen anything that looks like a door. What we'd like to do then is discover for our planner over here something that looks like an estimated cost to go, which is if in this location, where should I be going that would likely lead me in a sort of hopefully cost effective manner to get to the door itself, even though I don't know where that door is. And then the connection between what effectively becomes one image over here, which is our partial semantic 2D map, and another quote image over here, which is our estimated cost to go. And this is just image as a function of, is cost to go as a function of state location. And the connection between these two things then becomes the cost to go estimator, which is the fairly standard looking UNet with an encoder decoder. And of course, this is the part that we're going to learn, right? So again, just to summarize, the robot's driving around is partially discovering a semantic 2D map of the world. It wants to generate a estimated cost to go, and it's going to do that through this estimator, which is the thing we're about to learn. Okay, and once we have that, the cost to go goes into a standard MPC planner, and then off you go. And so it becomes a educated exploration algorithm, right? There will be a component of exploration that has to happen in this cost to go discovery here. But it's something that you would hopefully be heading towards the door in an intelligent way. And if you've done this type of work before, you know one of the major challenges is getting a data set for this type of work. So one of the things we were able to do was to get real house sort of overlays from the map. And so we don't just want to be using, that. We end up with sort of a semantic label of this, which becomes this map here. And so you could then compute the actual cost to go. And again, in this case, you know where the door is, and you can work out the entire cost to go. So this becomes the input for the learning algorithm. What Mike then did was generate these observation maps. And what these do then is obscure out large chunks of the world. And you say, well, in this case, what if all you knew was inside this white? So you overlay that on the semantic map, and you just get this little piece here. And then the cost to go ends up looking like that. And then now what you'd be learning in this case is the linkage between these two, the masked semantic map and the masked cost to go. This then becomes the input training data for this learning algorithm. So we don't have many real houses that we worked on, but we can apply many, many maps to them. So we end up generating lots and lots of training data, even though we have a very small number of actual maps to work from. And so you end up with so lots and lots of these two linkages up here. Each case, you're learning the linkage between the mass semantic map and the cost to go, the mass cost to go, and then you try to learn that linkage. And then you take that, of course, and go off and look at a whole bunch of other cases and do a sort of assessment of how well this is working. And so here's just some qualitative discussions, and you have sort of satellite images, the actual semantic sort of representation of those images. And then you can see things like, obviously the road, you can see things like the driveway, you can see the pathway to the door, you can see the house and things like that. None of this would be known to the robot. This is the true cost to go that you can compute using sort of a Dijkstra type algorithm. And then shown right next to it is the predicted cost to go. And you see an amazing, sort of qualitatively anyway, just how similar these two things look. There are cases that look a little bit different. This one down here where they're not exactly looking the same, but this is way outside the sort of, all these kind of look the same. This one looks completely different. And so this is actually an urban house that doesn't even have a driveway. And so this is way outside the distribution set and still working relatively well. And this just shows a similar thing, but it's thinking about it in a partial semantic map sense. So again, these are the kinds of things that might be known to the robot as it's actually doing the exploration. So that's the qualitative. If you think more quantitatively how things are actually going, again, the figure of merit here is just the extra time to the goal. It's sort of how long is it, it's not just how good is the picture, but how long does it actually take you to get to the goal, as it turns out, the door, even though you don't know where the door is. And this is just comparing sort of our cost to go with sort of frontier-based type exploration. There's typically quite a bit of variation in these results shown by the error bars, but you can see just how much shorter the green cases are. There's a bunch of different cases considered here, sort of houses right out of the training set, similar looking neighborhoods. Remember, we assumed there was quite a bit of structure in this problem, but you could go to like different neighborhoods and now houses that look quite a bit different. And then, as we said before, you go to urban where things now are getting hugely different in terms of, and yet we see things getting a little bit longer, but still sort of a fairly controllable, sort of reasonable growth. It's not a significant increase in computation time or to deliver. All right. So in a perfect world, we would have shown this outside. That was the plan for the spring. In this world, like all I can show you is this this map of the simulation, which is a little bit jerky because of the engine wasn't working 100% as effectively as we would like, the kind of simulation engine. The computer was bogging down with all the different things it had to do. What you're seeing here is the image of what the robot would see, right? This is the discovery of things. Again, what you see in the top right is the semantic map. This is, again, partial semantic map, an estimated cost to go that it's creating, which is then being fed into what the planner should do. And so this is all the robot knows. What we see is sort of a much bigger picture. We have a sense of everything over here in terms of how well it's actually doing. But again, this is really just showing the effectiveness of building that sort of partial semantic 2D map, which we can create by labeling things as we see them. And then through the things that we've learned that I just talked to you about, this UNet here, we can then generate a cost to go, which works into our planner and then generates a more effective sort of online planning strategy. Okay. Now that, like one of the last things we did just before sort of MIT shut down was, we had a bunch of different ideas in terms of directions. One was to go outside and do experiments, but this is about as far as we got, which is actually just open the door and drive into the hallway. So it's basically showing the same technology works on a real robot. This is now essentially performing the same function that I just described. You see some blobs over here that end up looking like the semantic map. And you can see I was labeling the different objects that it's seeing, identifying them as being similar. The colors are representations of similarity. We don't necessarily know what they are. We just know that they're similar. And over here, we're then creating sort of a semantic representation of that. And so it's indicative of this is hopefully going to work in real life. We just haven't had a chance to actually implement this yet in an outdoor setting. We've done tests of some of the components, but have not been able to run the entire algorithm outdoors yet. All right. So if I can get this to stop, one of the last things I want to do then is to talk to you about what work we'll be doing on what I'll describe as consistent multi-view data association. For those that have worked on cooperative SLAM or collaborative SLAM, the data association and then loop closure are sort of classic issues in a SLAM problem. And one of the challenges we've been facing is situations where we have sort of multiple robots, and I show them here as just cameras, but they're sort of looking at that world. There's a bunch of objects in it. They get disparate views of it, different perspectives, different lighting conditions, and they might come up with an indication of the things that they think they've seen. The question then becomes, are these actually the same things? And so What you want to do in terms of data association is actually try to find the linkage between them and come up with an indication of the fact that, yes, we all saw the Statue of Liberty, all saw the same Eiffel Tower. And if that's the case, then we can actually do the fusion. So the first part of that then is sort of recognition of that alignment. Are we talking about the same thing? And is it the same object? Can we now sort of recognize it's the same object, which is partly a classification problem, but given the classification, it then becomes an alignment problem. The challenge is that the observations are typically very noisy and incomplete, and that if you just did a pairwise association, which is the typical state of the art, you'll typically find sort of suboptimal and or inconsistent solutions that come out of the result. And so what we're trying to do then is jointly sort of take the entire set of observations across all the views that the robots have and try to rectify those errors in the pairwise associations and obtain a consistent association across the entire team. So the key insight that we had early on in this work was that cycle consistency, we can use that principle to try to rectify the errors and obtain consistent association. So in this case, you might end up with an association that's incorrect. And so there was a situation where C thought that there was a sort of, it made the correct association, but A and B and then B and C were able to then correct for that and identify that there was a problem and then remove the incorrect association that previously made. Now, again, you can formulate that problem as an integer program, but as I mentioned before, anytime integer programs are introduced, you want to be thinking computational complexity, and the challenge is these problems are going to be very large scale, and so that formulation will be computationally prohibitive for problems of that size. And again, the existing state-of-the-art joint solutions, i.e. the ones that are really trying to find these consistent solutions I've described, then end up either being computationally expensive and or inaccurate. And so normally you'd be thinking about these on a graph where you think about accuracy and sort of runtime. You'd like to have a smaller runtime in this direction, would be fast and have high accuracy. And I'll show sort of numerically this cartoon ends up being roughly correct. But basically when we end up in a situation where there's different types of papers and approaches, people will look at convex relaxations, spectral relaxations, and sort of graph clustering. And they sort of tend to follow these trends shown here, and there's some papers down here to think about. Clear, the algorithm I'm going to talk about ends up typically in the top right corner, and I'll justify that in a minute. So our approach, Clear, is going to leverage ideas from spectrograph clustering, so it's sort of in here, to obtain cycle-consistent solutions that will end up being computationally efficient and also high precision. Okay. And again, so the insight is that the problem has a graph representation. The objects that we're talking about are going to be nodes on the graph, and the associations are going to be edges. And that furthermore, if the thing ends up being cycle consistent, you should end up with a collection of disjoint clusters like this. So that's the premise sort of going in. That's the sort of the observation. One of the giant challenges here is you do not know the size of the universe. You don't know the number of objects you're necessarily talking about. So you have to have an object's sort of universe size estimator that you're actually going to be running and try to develop how many of these objects you're actually even talking about. So the approach to this problem ends up being a eigenvalue problem on a modified version of the Laplacian, which is actually part of the animation that's running down here. So if you're used to this notation, there's going to be a Laplacian matrix for this graph that you end up forming. There's a transformation that we do of that, which is described in the paper. The result ends up being a modified version of the Laplacian matrix. Do an eigenvector eigenvalue decomposition of that. The number of significant eigenvalues then, and again, that's described in the paper as to what that statement means, but that number can be used to estimate the size of that universe. And from the eigenvectors, then you go through a process described, sort of shown somewhat here in the cartoon sense graphically, ends up being a discussion of what the embedding would be for the cycle consistent solution. And so in this case, you end up in a situation where the eigenvalues will give you a good estimate of the size. The eigenvectors give you a good sense of what the clusters would be. And the result will end up being a cycle consistent association graph, which tells you which elements should be connected and which should not. Okay. So That's sort of at a high level what the algorithm does. Given that, you say, fantastic, but how well does this work on classic benchmarks? So you pull up, an example here. This is the CMU Hotel, which is sort of apparently a classic benchmark problem. You look at a bunch of images in that movie, and you start making associations between them. A cycle consistent association here would look like a triangle, right? It looks like I'm associating these dots between the three images. An inconsistent association then is shown here in red. And so again, you're going to end up with a bunch of pairwise associations that are being made. You feed this into an algorithm, and there's a bunch of algorithms out there. And the question ultimately is, can you clean all this up? And can you come up with the cycle consistent solution that in a computationally efficient manner? So graphically, then you would have to think about there's three things we're going to care about here. There's the precision, recall, the standard things, and then what I'll call rate, which is an indication of how quickly you're doing this thing. And ideally, we set these graphs up in such a way that you want to be on these plots. You want to be in the top right. You want to be up here. And not too surprisingly, as I indicated before, clear is actually up here. And the distinction on the dot color here is that the green is a cycle consistent solution, whereas the red is not a cycle consistent solution. And so we have a situation here where there are some algorithms that are actually close to clear in terms of, say, this plot here. But that's over here. If we look at, say, the computation, it turns out that clear is about 21 times faster than this algorithm right here. And that's captured, still captured. I guess the computation here is actually logarithmic. So they look close, but it's actually pretty far apart computationally. And down here, clear then is sort of top right compared to the others on the precision recall. So in summary, clear, the algorithm we're talking about here improves both precision and recall of the input data set. So it's that's shown by the baseline orange lines here. We're up on top right, superior to all the other algorithms. And these results up here are indicating is way, way faster than the other types of algorithms that exist. And again, a lot of these algorithms come out in the past couple of years. And so they're quite recent. So that's thinking about the multi-view. Of course, in some situations, you might be flying around as in a forest. And I hadn't realized how easy it is to get lost in a forest till you started doing this problem. Where in this situation, we're using the trees as features, but a lot of trees look very similar. It's very hard to figure out precisely where we are in this forest. And in particular, make a connection between these two robots and actually figure out either as a given robot, have I seen that tree before? Or if there were two robots flying around, have we seen the same tree? And so it's a situation where you'd like to be able to do that assessment of are these the same or not in the actual analysis for an individual or a multiple robot. So lots of stuff on this plot, but I wanted to give you a sense of just how messy this is. Again, red lines here are indicative of just bad association. So you're flying along, you see a tree, you think it's the same tree as so before, you make an association with tree up here and a tree way down there. Just really bad, lots and lots of bad associations being made here. So a horrible data set is an input. You run this through the algorithm clear, it cleans things up dramatically. There's a couple of sort of remaining red lines, which end up just being mismatches that are left just simply because you don't have a lot of data supporting either yes or no on these. They're relatively easy to prune out. You just look for situations where the sort of low redundancy situations, or just small clusters, you can just get rid of them without any impact on the algorithm itself. And the result then is a situation where post-processed, it looks very, very clean. Now you can try all the other algorithms on this, and again, they end up doing a pretty nice job on cleaning up on this baseline. And as you might expect, they're pretty good algorithmically, but computation time is a significant difference between clear and the others. And it's a dramatic improvement even on the quick match, which is the next fastest. So of course, when you take this and feed it into the algorithm, if you were doing baseline and you had all these wrong loop closures, of course, you end up with just a disastrous sort of estimation of where you are located, as shown by the red compared to the blue being truth. But if you clean that up and come up with the correct associations as clear as finding here between all the different trees, then you can end up with a very, very nice estimate of where you are. And again, that's thinking about it in a single robot flying in a world where you have a hard problem to do loop closure. We've also been thinking about situations where we have multiple robots. There again, we're running in a simulated environment. We're finding lots and lots of cars here. So we're identifying these as quote threats, but they're just objects in the world. we're driving around, and what we have is 5 agents sort of driving around in this simulation world with a fair amount of overlap in the different trajectories. And the idea is, can we come up with a consistent count of just how many objects were there in this world? And that's done. There was a total number of associations done on the order of 1,000. And we then run the different algorithms through the data sets and come up with an estimate of what's going on in terms of the number of cars that actually exist. And again, the first thing you have to do is to estimate the size of the universe. How many objects are there? And there are techniques for doing that. Eigengap is a standard state-of-the-art technique, but it failed miserably and basically came back and said there were as many as we saw, which is just over 1,000, which is pretty useless. The truth is much closer to 35, and Clear actually found an estimated number of 38. These are the same graphs that I saw before. So once you've done that estimation of the number of objects, you now move on to the sort of actually trying to make the linkage between them and come up with estimates of sort of start clustering them together. And you now start comparing again on precision rate and precision recall. Again, the 3 axes we described before. Again, Clear sitting at the top right up here, top right in this graph as well. It's relatively close to match ALS, but again, remember that this is a red dot, meaning it's not a cycle consistent solution. And so we have a situation where if you post-process that, which they describe in their paper, you can actually get to a consistent solution, but with a significant drop in precision as a result of that. So again, just to summarize, I mean, Clear is getting a good estimate of the number of objects in the world. It's faster than a lot of the other algorithms, much faster than some, a little bit faster than others, but it has the best precision recall of all the algorithms that we've looked at that exist in this domain space. So the caveat on this is that it's currently centralized in what I've shown you, and it's sort of relying on good network quality. It's sort of operating on the axes of quality and sort of how well connected are you to a centralized server. We're sort of operating up here in the top left. We're assuming good network quality and that we aren't disconnecting very frequently. We, of course, would like to be able to operate sort of down in this range with bad networks and or longer periods of disconnect. The work we've done recently is moved into this domain space where what we're thinking about is a distributed implementation of that algorithm. We've already created this. It's about to be published. And it yields actually the same accuracy as a centralized solution. This is work with Costas at UPenn. And so it's for situations where when the robots become disconnected from the base station, you don't necessarily have access to that central computation hub. You now then are still able to implement a distributed version of the algorithm, even though the vehicles themselves may have limited computational capacity. You distribute that calculation, they can now come up with a similar estimate of the same estimate that they could done centrally. And we've also been extending this to think about the inputs as no longer just being the features, that one sort of object classification that we've described before, but instead thinking of it in terms of matrices. And the reason for that is to actually expand this to actually doing classification on things that look like point clouds. And so we're actually expanding the framework to provide additional information from the matrices. Should enable us to then do a much better job of the data association and improve the accuracy of the actual SLAM algorithm, where again, the objects now are getting generalized from just points and sort of one binary up to now essentially an entire point cloud at a given location. All right, so I've covered a lot of ground, but as I've indicated at the very beginning, there's lots of things we're working on that I didn't get a chance to talk about, but what we have had a chance to talk about is some fast and safe trajectory planning in an unknown environment when we have access to sort of a view of the world that's revealed to us in real time. We've also thought about how to expand that to planning beyond the current field of view when we have availability, say, a learned context that we can use to not only look at what is around us, but also what that infers perhaps about the cost to go and how to get the goals that we may not be specified to us in a spatial sense. And then thinking about some of this work in the multi-agent sense, how to align and then fuse these local observations to come up with a very high precision, computationally tractable algorithm that is can then be used to actually then is a precursor to a lot of the collaborative SLAM, loop closure, and the consensus type algorithms, where we have agents that would like to do a fusion, but first have to agree on whether or not they're talking about the same objects. And so in any one of those steps, the first thing to do is the alignment, and then think about doing the fusion that follows, either as a loop closure or as a consensus algorithm. And with that, I'll stop, and I appreciate your time, and look forward to questions.
Thanks so much, John. That's amazing stuff. Okay, so we have a few questions coming in. The first from Juan Camilo Gambaro Higuera: would CLEAR be applicable to multi-camera, multi-object tracking where cameras are fixed and tracked objects are visible from vastly different points of view?
Yeah. So definitely in cases where the cameras are fixed and different fields of view, I mean, there's always going to be an issue in terms of how well one can do an association. The assumption going in is that the data going into these algorithms is pairwise associations. So you would have to first do that, and if you can do those pairwise associations, sorry, I was trying to go back to here. Then you use CLEAR to sort of clean up. The premise is that the pairwise is good but not great, right? And so if you have very disparate views, you might have situations where the pairwise are just doing a really miserable job of actually connecting and linking the different views of these agents. So you might find situations there where, similar to what we were finding in the forest, we're just getting a lot of really bad data going in. As long as you have some signal inside that bad data, then CLEAR can sort of decipher precisely what's going on and then figure out what the correct associations are. So the short answer is yes. The long answer is I think we'd have to take a look at exactly the data set to see whether or not how good the pairwise associations are as input.
Great. Yeah, another question about your thoughts on using RGBD, like depth from a CNN, as a replacement for RGBD camera sensing. Have you tried to do that? Have you done any visual navigation with pure RGBD? Pure RGB sensing.
Yeah. So using RGB instead of RGBD.
Yeah, and predicting depth with a deep net or something.
Yeah, good question. So we've done a little bit of work. I actually had a visiting student here from Spain a year and a half ago, and he was looking at sort of pure vision. The challenge typically with the challenge with vision is extracting depth, right? And so the real benefit of an RGBD is that you get the depth for free, and then the vision sort of tells you what's in the image, and the depth tells you where it is, and the combination of those two is just great. If you're trying to run the processing to figure out depth, you have to extract depth from a single image, and that's not impossible, but challenging. If you can do a learning algorithm that can extract depth from the vision, and then you have that separate channel that's taking just the RGB and then running, the neural net to then extract depth from that image, then you will have that the same ability you get from an RGBD camera. I'm not sure how well that works though. I mean, I've seen it work well. I've seen it not work well. And it just is so dependent on things like lighting conditions that I think it's a very difficult case to learn in a generalizable fashion, in my experience.
Awesome. We have a question from the other program chair, Michael Brown. For the Cost2Go work, the input is a single channel 2D semantic label map. Could this be expanded to be multiple labels with probabilities, e.g. top two objects plus their associated probability? Like, could you have a posterior over objects rather than just a maximum likelihood object?
Sure. I don't. Yeah. I mean, this is what we were doing, but I think there's certainly, as with a lot of these learning algorithms, the more you can bring to the table, than in terms of input, then you can learn from it. We essentially were learning from one image to another. If you can generalize that to sort of a three-dimensional image that has another aspect of probability on top of it, then yes, can definitely add that in. It's more complex, but it certainly would typically be a better representation of what would actually have in terms of classification, right? So it wouldn't, Because even in the labeling, you don't tend to have absolutes. It's not like it's 100% this, 100% that. It tends to be with high probability it's this and low probability it's that. So if you could take what you actually have coming out of your classifier as the input to that 2D semantic partial map, which you then learn the cost to go from that, which I think is what you're describing, then yes, that would make sense as a sequence instead of what we did.
Yeah, so quick follow-up on that. So the mapping from semantics to cost to go is like, there's no probabilistic representation in the cost to go currently, right?
Correct. Yep.
So is there any way to incorporate uncertainty estimation like directly inside that cost to go map?
Well, let's think. I mean, what the planner is expecting is a cost to go, right? It's not so. So this is so again. I mean, let's be clear what we're doing because because the short answer could be yes. It's just that what we're doing right now is a deterministic MPC planner that's looking for a number, right? So I could put probability in this estimated cost to go, but then it's going to go to the planner and it's going to throw his hands up, so what am I supposed to do with this, right? So if you generalize the planner to be more about like it was robust and understood probabilities, and maybe it was, think about either, sort of there's different ways of robustifying the MPC, and think about different types of estimates of the cost to go. In which case, you could then have the estimated cost to go become more probabilistic, or become probabilistic. I mean, it's not, but in what I was describing just now, what I was describing was change this picture over here, and then learn a different encoder decoder, and end up effectively the same picture over here, a same deterministic cost to go. I think what you're now describing is change both of these pictures to make them probabilistic. I.e., this would have some element of probability about labeling. This would have some probability about success. It's a question of I can imagine you doing that. I just don't know what the planner would necessarily do with that. I'd have to sit down and think about, typically you want to start here at the planner and say, here's my planning algorithm. This is what it's expecting in terms of the cost to go. Where am I going to get that from? And I'm not sure that I'm aware of too many algorithms are looking for probabilistic cost to goes. So if there was one and we needed one, then we can probably make one.
Yeah, there would have to be some payoff at the end of the day.
And I'm not saying it's easy. I'm just not. I don't necessarily see a problem in doing it, but I'm not sure what in the current formulation I couldn't use it. But I'm also not sure what that formulation would become to enable us to use it. So I have to. I mean, I've worked a lot on robust MPC, and there's certainly things like cost to goes that are thinking about sets and things like that. But typically we're thinking about planning in an MPC sense. I'm going to arrive at a point and want to have a lookup map that says if I arrived at this location, what do I estimate my cost to go to the goal to be from there? And so I really just want an estimate of what's going on. And so it for us it ended up being a number, right?
Makes sense. So another question related to 2D versus 3D representation. So a lot of the work that you've shown is like 2D representations like this, but at least the experiment that you showed with the quad, it was navigating in a 3D world. So what's your feeling about 3D problems? Have you worked on 3D problems, planning in 3D, and what about a network of mine shafts type of idea where you have to do a full planning problem in 3D?
Yeah, I mean, this work ended up looking 2D-ish, but it's like I sort of stopped at this picture to highlight the fact that it's not. Everything that was created is done in 3D. It's just that you tend to sort of show examples and things like this that are all 2D just because that's what it is. It's easy to show what's going on. But I mean, even here you can see the paths are three-dimensional, right? The object is going up and around things. But it's explicit when it's flying in this world that it had to fly over stuff and under stuff and around things. So you see it going up and down and things like that. So this is a three-dimensional planner that's typically shown operating in in simulation roughly 2D, but in these experiments it's explicitly 3D. but yeah, like you say, if you're doing a mine shaft and things like that, then this is definitely a three-dimensional representation and requirement. So it would have to be a planner that's able to go up, down, and so on. And this does that. Right? So it's sometimes presented in such a way that it looks more 2D-ish than it is. But as indicated in these ones here, I mean, this is if you look in the, sorry, I was trying to show this one, the multi-vehicle one. This is explicitly three-dimensional, right? I mean, you see the paths here going up and down and all kinds of things. So this is a variation of faster. It's not exactly the same thing, but it's using many of the same technologies. And like I said, it's explicitly a three-dimensional planner.
So we have a question from Greg Dudek. So this is a bit in the weeds, but field experiments are usually very noisy. Given the overlap in the error bars in your planned assessment, in your planning assessment, how do you address the question of statistical significance? I'm not trying to be adversarial, since real field experiments often face this kind of issue. The obvious answer is do lots more experiments, but that can be infeasible in practice.
Was it this graph or?
I think this is the one he's referring to, yeah.
Yeah.
The fact that there's high error bars and it's very hard to, like, you're only taking a sort of small number of samples, I guess, from the real world somehow.
Sure, and I think, you know, I think this was done, you know, we created a representative set of different neighborhoods and tested them. They definitely overlap, but I mean what's shown here is indicative of the fact that there's a mean value, and it's sort of like a box plot, right? So the significant mass of the experiments are shown by the color bars, and the breadth of the values are shown by the gray lines. So there is variation in the two results, but on the other hand, the mass of the results differ substantially in the green versus red. So I mean, it's one of those things where I think whenever you see error bars like this, you have to think about, well, in that particular example, how did they differ, right? And it's, you know, if they were more similar, then I would have expected the significant mass in the red and the green to be more similar in height. In the sense that if you took any particular example and they were quite similar, then I wouldn't have expected such a big difference here. But I appreciate that. Yeah, I mean, with large error bars, I think you'd have to do more experiments. But I don't know that we want to do more simulation experiments. And what we wanted to do was more outdoor experiments and actually sort of move this into a domain space where we're able to show that the things that we think we can discover semantically and then convert those into a cost to go map transition to real life experimentally through the actual camera of the vehicle was, I think, the harder issue than just simply whether or not the planner is doing better. Because I think there's strong evidence to us that the planner is doing better. It's just that the key issue is, you know, if you continue working in simulation environments that look like this, you know, there's only so much you can demonstrate. You really need to be able to move out to the real world. And that's basically what will happen, hopefully later this year when we get back to campus.
Great. So we had a question about the Beyond Horizon Planner compared to the Frontier algorithm.
Yep.
So assuming that your algorithm runs on a GPU, did you also put the Frontier algorithm on a GPU? Maybe.
Good question. I unfortunately don't know. So I can talk to Mike and find out. I don't. I'm trying to think whether or not. So I assume it's running on a GPU. I'm just trying to think. I don't think algorithmically they would have been implemented differently. I mean, in the sense that they. I'm trying to think what computer is even on there. But again, this isn't so much about like when I say time to goal, it's not really a computation time. It's an actual like driving time, right? It's how long does it take the object to get from the beginning to the end. And I think the computation time is sort of being somewhat ignored, which if you're doing it in simulation, you can do, right?
Right.
So it's not like the robot's just sitting there computing answers and then we count the wall clock time. This is simply the driving time.
I actually had a question about faster, if I might jump in. So I've seen a few other works. So like in the forest example, it wouldn't apply, but in the structured example, it would apply. Some works that have tried to actually predict what the unseen space of an environment looks like based on structure that exists in the environment. Have you
Right.
guys looked at anything like that? It's particularly applicable to fast motion planning, right? Where you could make a pretty good guess
Yep.
of what's around the corner based on having seen a million buildings before or whatever.
Yeah, well, that would be like taking the second part of the work and sticking it on this part, right? It basically says, this is how you fly quickly in an environment if this is what you can see. But if you could take what we did with the ground robot and stick it on here and say, okay, but given that this is what you can see, can you actually extend beyond that? So you could certainly do that. We haven't done it, and you probably knew that we were thinking about doing that for the FLA project that sort of preceded this. Um, and one of the challenges simply was just how well could we see. There's a difference in my experience of a ground robot using sort of a camera semantically label things when it's sort of trundling around on the ground versus what I've seen on a quadrotor or semantically labeling things. There's such high agile motions that in my experience, it's very difficult to actually see anything long enough that you can come up with a semantic representation of it. We're sort of more in the mode of there's objects there, let's fly around them, and as soon as you then turn, don't see them anymore, and you just don't see. So you see snippets of objects long enough to actually discover that they exist, but we don't have great long duration looking at them to come up with semantic labels on them. But I mean, your point's well taken. I mean, there is if you're concerned about the depth of our image, and we're seeing here about 4 or 5 meters in front of us, if there's a possibility to extend that by a meter or two by coming up with a good estimate beyond that, then sure, it would make sense to consider that as well. But again, you can imagine situations like the office environment here on the right that we're showing. It's a question of what are you actually able to extract from this image? Because when you fly around in that environment, the robot sort of sees the things on the left here, and some of them are looking like doorways and things like that, and they may be indicative of a hallway, but they may be indicative of an office. They just don't really know. But if there was a way to add that information in, then yes, it would make sense to do so.
Do you have like a hard stop at some point, or can we keep asking questions?
Like 1 o'clock. I think we're good.
I had a question. I mean, I think these questions comes up a lot. You've probably heard it before. What are your thoughts on combining optimal planning to efficiently reach a goal with RL that seek to learn traversability, or I guess even more generally, the role of optimal control and RL now with RL being such a
Yep.
prevalent paradigm.
Yeah, we're actually starting a new project on traversability this summer. So it's sort of higher speed ground driving. Well, I mean, optimal control is the optimal answer if you have a model, right? And if it's not, then it's, well, what's the model? And I've spent an entire career struggling with the answer to that question, which is, if you give me a model, I can give you an answer. But the model, the statement, what's in that model, for me, used to just consist of the vehicle dynamics, because I was just sort of, that's what I concerned about. Now you start thinking about the world, right? And the reason that we started thinking about deep RL as a collision avoidance algorithm was the complexity for us in modeling that world wasn't just about the vehicle dynamics. They were almost trivial, right? The complexity was everything around it. I mean, it was, how do I model all these people? What are they doing? Where are they going? And so the problem there of optimal planning became one of thinking about that model, not necessarily thinking about how to pose the problem, because we're working with other collaborators that are hard and fast on thinking about NPC as the algorithm. We can predict all the objects around us. We can predict where they're going to go, and then plan a path through it. And that's when I started doing this work, probably 10, 12 years ago, that's exactly the strategy we were taking. NPC continues to get faster and faster. Our ability to classify and predict gets better and better. So at some point, that approach will become, I wouldn't say necessarily, I'm not sure the right word to describe it. I mean, it's sort of, it was intractable previously, possibly becoming computationally tractable and in a meaningful sort of performance sense in the future. But as I was describing in the work that maybe I flicked past too quickly in Mike's stuff here, this picture here is sort of a general concept of, look, yes, you can do end-to-end learning from data in to actions out. You can do that, and people do, and I've done it. But the reality is that there's a lot of algorithms that exist that are quite good at doing things like optimal planning. If you give me a model, SLAM, I can do, and occupancy grid type calculations I can do. So the whole point really of what was here was to think about, let's pose the learning problem that actually makes sense. And as often when I talk to students, it's like, I don't want you to just say, I'm trying to solve this problem, let me do it by using RL. It's take the techniques that exist, demonstrate a limitation of them, and then think about how learning or RL could be used to either solve problems that are perhaps not well known here, i.e., in this case, what was the cost to go calculation, and or think about, maybe I don't know the dynamics, maybe I have to learn the equations of motion of the system or parameters in the system to describe what the model is, and then I can fire up an optimal planner that I have. So, I think we see these challenges in a lot of papers that show up at conferences where RL is used as the solution, where it should really be viewed as part of the toolbox. And there are a lot of other techniques that are part of that toolbox as well, and things like optimal planning is one of them. So anyway, you answered my philosophy on where it fits. That's
Personally, I completely agree. Yeah. So,
yeah.
okay, another question from Ren Cheng. Question about the cost to go map from the semantic 2D map. How do you deal with the possibility that you have overlapped objects? For example, a bridge above a crossing road or something like that. That would be different.
Good. Yeah, good question. Well, the good news is that not many houses have bridges, so we've not had that problem. The big challenge here was actually getting from this step to this step, right? I mean, because one of the reasons why you only did 77 real houses is that if you understand what's involved in going from a satellite view like this to a semantic map that looked like that, is that someone actually had to sit down and semantically separate all these things out, which you can do somewhat algorithmically, but then someone else had to label it. And so this is actually quite expensive to do as an operation, either in terms of student time or actually paying somebody to do and go through and semantically label this. Now, in this situation, if we had, say, bridges over things and things like that, or overlapping objects, you would have had breakages in here in terms of what the actual labeling was. And then you end up with a classic learning problem, which is that if it's bad data going in, you might learn poor things coming out. And so I'll say up front, I don't think we have a good answer to that problem. It's something where our data set was constructed in such a way that, I think the student actually paid for this service to be done and then went through and checked every one of these to make sure that the data set going into his learning algorithm, and again, his focus was on putting these mass on it to break it up and make it into a sort of, because he's learning the mass semantic to mass cost to go. And this data over here was just simply sort of a giant pot that was created. It wasn't huge, but still took quite a bit of time to do. And then from that, he was able to go off and learn. So if you had overlapping objects over here, it necessarily wouldn't have worked. Now, in real life, right, you'd be actually going underneath things, right? So you might be going under a bridge, or you might see objects. And in that case, you'd have to rely on your classifier to be able to separate them out and actually figure out what's going on. And then that partly, I think, goes back to that discussion we had earlier about probabilistic classification, which ultimately is going on here in the sense that you're not going to label something unless you're really confident in it. But I think we're already gone past the point where we're saying we're above a threshold, so now we've labeled it. If you're approaching that threshold, you might have been dealing with a probabilistic labeling, and you might then have sort of, it could be this or it could be that, and you might also want to develop a cost to go when you're still at that level of uncertainty. And you'd have to deal with that, I think, also if you had these overlapping objects, because that would tend to confuse things even more.
Yeah, in some sense, it's a limitation of the satellite view, I guess.
Yeah, well, yeah, I mean, an overlapping sort of a from above is, but overlapping from below would also tend to happen. There would be objects behind each other, but even just objects sitting next to each other, and you wouldn't necessarily be able to distinguish between the two. But those are, I'm not trying to sweep them under the rug. Those are challenging classification problems, but the challenges that we haven't faced yet. I don't think it means we can't do them. It just means they haven't been part of the problem we've been looking at so far. And if we wanted to take this into the real world as we do, I think there are other challenges we'll discover as we get there. It's just that they haven't been part of what we've discovered as being the problem. This is sort of just at one layer, create a solution, demonstrate that this is working well enough that it makes sense to go on and try the next piece. And I'm sure we'll discover new problems when we get there as well.
Awesome. A question related to clear. Is it possible, or do you know of any work that uses learned feature encodings to improve the association without compromising efficiency too much?
Oh, I don't actually. So I can, I can get you in touch with Keve, the postdoc working on this. I mean, these are the papers that he's been comparing to, Roberto is at BU is probably the most recent work in the quick match that he developed, and that's he was part of Costas's group. So that's sort of, I think, our exposure to the probably the best of the strategies that existed prior to what we did. So if there's other things we should be looking at, then please send us an email and let us know.
Cool. In faster, how do you account for vehicle dynamics?
Faster. Sorry, keep flipping back and forth. Sorry, the other vehicle dynamics or our vehicle dynamics?
Your vehicle.
Let's see. So we have, so again, sort of somewhat sort of, sorry, I have to get back to the, so embedded in the MIQP is this formulation here. So we have a jerk constraint, we're sort of minimizing jerk. We have sort of a description of the path we think the object's going to be able to follow, which ends up being the Bezier curve. And so basically what we have is a sort of understanding of, from a vehicle dynamic perspective, how well it might be able to fly a curve of, say, a particular curvature and things like that. So jerk constraint, I think, is sort of this, I would say necessarily is the state of the art. I would say it's beyond the state of the art, but it probably is the state of the art in terms of the standard ways that people now are costing these types of designs. So it's not, sort of even velocity constrained or velocity optimized. It's thinking now about, sort of the derivative of acceleration, getting up in a jerk. And so that through the parameterization of these paths here, the A's and B's and C's, we can now come up with a representation of, given the vehicle dynamics and what it's capable of, we know what type of path it would be able to follow. So the dynamics end up being captured through this representation here. So it's not like a one-to-one match. I mean, it's not like we're writing that F equals ma and thinking about all the vehicle dynamics at that level of complexity. But in a lot of these path planning algorithms, you can't do that, right? I mean, we just have a sense of how fast it can go, how much acceleration it can handle, how much jerk we expect it to be able to handle. So these types of constraints go in, and then we can sort of say, we essentially know, I mean, the main limitation for us, I mentioned before, is just how quickly we can do roll and how quickly we can do pitch. But again, we tighten the attitude loops really, really high, strongly. So it's very aggressive on attitude. And so as a result, we can essentially ignore how quickly or how much time it takes to do roll and pitch. But we are looking at these max values down here as constraints we can put on that actually limit how much this is able to vary.
So yeah, maybe one last question related to faster, I think. So this work, it has a balance between safety and efficiency. And so in general, these two things are pitted against each other. So in some general sense, what's your thought about the balance between safety versus efficiency or speed of robotics, and how can we optimize
Yeah,
that?
that's a good point. It's just that, if you're building a quadcopter and not being safe means you whack into stuff and then you're picking up pieces off the floor, you tend to shift the balance towards safety pretty strongly if you're the grad student. But that said, if you were operating around people or in vicinity of things, I think you need to be able to think about a safe state, a safe way of driving. When we were doing the work with the robot driving around in the environment with people in it, there were notions there that of sort of adaptive safety, right? That if you have a sense that with the world around you is relatively clear and empty, then it's quite likely I should be able to speed up to perhaps a higher speed that I could safely stop from, in a normal situation. So then you can imagine taking Vmax, cranking it up a bit, and then just again being very vigilant and being aware of what's going on. But that robot has a much longer field of view, and it's got a LiDAR on board, and it can see 10, 15 meters. With a quadcopter flying with RGB sensing, you know, I mean, you only got a couple of meters. It does take quite a bit of time to rotate, and the result is that you have to be pretty careful in terms of safety there. So, you know, if you start thinking about performance and really emphasize this over safety, you'll just end up picking pieces up off the floor almost the whole day, and that's not a lot of fun. And that quadcopters with a lot of glue on them don't fly very well, is my experience. So it's you know, there's only so many times you can glue things back together, and then you just build a new one. So you know, I'm not trying to be glib about it. It's a great question. I think that, you know, there is a tendency to be I wouldn't say overemphasizing safety, but if you put too much emphasis on safety, then the performance does get penalized. But you need, you know, probably another algorithm sitting on top that can be providing you that observance that says, these are situations that lead me to believe that if I can change the balance between these two parts of the algorithm, you know, there's some other evidence that suggests that that's the case. And like I said, when we were doing FLA, which is fast lightweight autonomy, so GPS denied navigation through a forest was sort of the problem. But occasionally you'd be in a forest and then not in a forest and then in a forest again. And you can imagine situations where if there's evidence from your sensing system that, hey, there's no trees around me, then you could take Vmax up to like 10, 15 meters per second. But there's no way you want to be flying at 15 meters per second inside a forest, right? That's chaos. So that literally was a case where we've had that sort of that other sensing capability, forest, not forest, that we're able to infer from looking at the longer field of view sensors. And from those, we can infer you know, how to change that knob and dial it back and forth. And that would be my strategy moving forward, I think.
Amazing. Look, thanks so much for doing this and for answering all of our questions.
Sure.
This was a fantastic presentation. I thoroughly enjoyed it, and everybody else on the Slack and on the YouTube is saying how much they impressed it. So thanks so much, and yeah, we'll end the stream there. But I assume if people have further questions, they can.
Yeah, please send me email. I'm in quarantine, so I have lots of free time, right? So, guys, stay safe. It's been a lot of fun, and thanks for your time and attention. Okay.
Great.